We explored recursive strategies in the last few videos, but when do you optimize a recursive solution further and how do you even do it? Hi, I'm Piyush, and in this video we are going to explore dynamic programming using a powerful strategy or a powerful optimizing strategy called memoization. So let's get started. If you haven't already watched my earlier videos on recursion, I would highly recommend that you check it out because we'll be building on top of the recursive leap of faith strategy that was discussed over there. We'll tackle two more recursive problems in this video and we'll try to optimize them further using dynamic programming, and we'll see how it significantly improves the time complexity with just a bit of space trade-off. So let's get started. Let's start with our first problem where we are given an array of numbers and a sum. And we need to find the number of ways we can form that sum from the numbers in the array. Each number in the array can be considered only once. For example, for the sum of 5, given this particular array, we have 3 ways to form the sum. Cool. Now let's devise a recursive strategy for this problem using our recursive leap of faith method. Let's move to step 0 where we discuss the subproblems we can investigate further. So we have n elements in the array, right? And let's say we have to form a sum of m. How do we divide the problem into smaller subproblems? Now that is something that we need to figure out. The first intuition that I have is that there are n positions from the n elements in the array, and a particular sum can be formed by some of the elements in this array by either including them or excluding them. So we can have a possible way by including 6, where every solution will have 6 as one of the elements adding up to the sum of m. And we can also exclude 6 to ensure that we also consider all possibilities of numbers that sum up to m without the nth element 6 present in them. Now that means that there are 2 possible ways for each element. Either we select it or we don't select it while finding a way for the sum of m. That is, there are 2 to the power n possible options, and we need to find all these possible ways and consider only those that actually sums up to m. To rephrase, we can either include the nth element to find all possible ways of finding the sum with the nth element included as part of the sum, and we should also exclude the nth element to find all possible ways of finding the sum without the nth element present as part of the possibilities. To visualize this, if we include the nth element, we are essentially fixing it as part of the solution. So to find the number of ways we can reach a sum of m, we now need to find the number of ways we can find the sum of m minus the nth element using the first n minus 1 elements. This ensures that the nth element is counted in the total possibilities. On the other hand, if we exclude the nth element, we can simply look for the number of ways to reach or to form the sum of m using only the first n minus 1 elements. So to formalize, we can go ahead with 2 subproblems. That is, if we include n, we can recurse with finding the sum of m minus the nth element using n minus 1 elements. And if we exclude n, we can recurse to find the possible ways of finding the sum of m with n minus 1 elements only. Now let's define the function state and what it's supposed to do. As discussed in the earlier videos, this will be a simple step, and we can define the function to simply find the number of ways to form a sum of m elements with the elements from 1 to n in the given array. Now the state of each recursive step is given by n and m. Keep a note of this since this will be useful when we are optimizing it further. Moving on to step 2, or the recursive step, where we take the recursive leap of faith to recurse onto the subproblems identified. So we will either include n and recurse with sum as m minus n with n minus 1 elements remaining, or we can exclude n and find possible ways to sum up to m using n minus 1 elements. Now in the next step, we'll take the inductive step to solve for n. That is, we simply combine the results from both of the subproblems and return the final value. Now we can also simplify the statements into a single return statement, just for simplicity. Now it's time to identify the base case to finally end the recursion. For what states can we say that there is no need to divide it further? Of course, if m reaches 0, we can say that we have included a set of elements that sums up to the original m. That is, we have found a possible way. This is one base case. Now, if m becomes less than 0, maybe we have subtracted a large amount previously, and we can say that a solution cannot exist for this m. And if n becomes 0, again we cannot go further anymore since there aren't any more elements left. Note that I'm using array elements index from 1, so while converting the algorithm to code, we will have to change the values a bit to make sure that the array is 0 indexed. Now let's add this to our code. So if we have found a solution, we return 1, or else we simply return 0. Let's now use an example to visualize the recursion tree before we explain the need for any other optimization. So with n as 3 and the sum as 5, we find the number of possible ways of forming the sum by including the third element and by excluding it. Now with the third element included, we again do the same, where we find all the ways where we include the second element and we find all the ways where we exclude the second element, and so on. Finally, we reach the base case where m equals 0. Now the time complexity for this problem is again similar to the one that we have seen in the earlier videos of recursion. That is, it's an exponential complexity of big O of 2 to the power n, since there are two possible cases for each recursive node, and there can at most be n such levels bounded by the array length. Just to recap, each node with n elements is calling two functions with n-1 elements, and so on. So there can be at max n levels till we reach the base case, and for simplicity, let's consider that the best case is when n equals 0, which will simply return 1 or 0. Now the second level will have 2 nodes, the third level will have 4 nodes, and finally the last level will have 2 to the power n nodes. So the total nodes in the tree is 2 to the power n plus 2 to the power n minus 1. And note, for binary trees, or rather complete binary trees with n levels, we'll have the total number of nodes till the last level as 2 to the power n minus 1. So the total time complexity becomes big O of 2 to the power n. And the space complexity is big O of n for the recursion stack in use. Now let's consider another example with n equals to 6 and m as 20, or the sum to be found as 20, with the given array as shown. So if we trace the recursion tree with each node having 2 options, we see that there are some states that have been processed earlier as well. For example, here n equals 3 and the sum as 16 was already processed when we had included the 6th element earlier, and we are again finding the same state when we are excluding the 6th element. Now this kind of states are called overlapping problems. Now the intuition is that if we can simply cache the results of a particular subproblem when we first process it, we can simply use it when we see the states again, right? Now in a different context, if you were given an array and you have devised a subproblem which was independent, maybe part of a divide and conquer algorithm, probably caching wouldn't have helped you. But for this overlapping problems, we can simply cache them. Well, so we can declare a cache for the states denoted by n and m, and we can have a map or a memoization table of size n cross m to cache the results of the state and use it if we see the same state again. So we are now introducing a new step, step 5, where we simply go ahead with the optimization and caching of the results. For this problem, we already have an algorithm defined earlier. We'll simply update the algorithm to include the global cache to be used for storing intermediate subproblem results of a particular state. And we'll add a check to see if this particular state was already processed earlier before we jump on to processing it again. So now if we trace the recursion tree again for the example found earlier, we will simply cache the result for the state n equals 3 and m as 16, so that the next time we get a similar state, we will simply return the value of the cache. Now there are n cross m states, and each state computation takes a constant time, making the time complexity as big O of n cross m, while the space complexity will become big O of n cross m for the memoization table and big O of n for the recursion stack. Feel free to visit trilab.io's problem set for more such problems that I've curated myself based on the problems that I have solved during my FANG interview preparation. So do check it out and you will find solutions and code snippets in C++, Java and Python in the problem sets as well. Now let's look at another problem or a variation of the problem that we just solved, and we'll try to optimize it again using the same strategies that we defined earlier. Let's get started. So now we are given the same array with a sum, and we need to find the minimum number of elements required to find the sum. Now this is a bit different from the thing that we have already solved, where we had to find the number of ways to form the sum. For example, when the sum required is 5, we have 2 possible ways and the minimum number of elements is also 2. Let's go ahead and investigate the possible subproblems. Just like we saw in the first problem, given n elements for each position, we have 2 choices. We either include the current element as part of the subset that adds up to m, or we can exclude it and continue checking with the remaining elements. This binary choice at each step is what drives the recursive solution forward. So this means that there are 2 options for each position, resulting in 2 to the power n possible candidates. We must select the minimum number of elements from this candidate set. Now, as we have seen earlier in the first problem, if we include the nth element in the current candidate, the subproblems we need to explore is how many elements does it take from the remaining n-1 elements to make a sum of m minus the value of the nth element. Now, if we exclude the nth element from the current candidate, we need to explore how many elements does it take to form a sum of m from the remaining n-1 elements. We can then take the minimum of these 2 subproblems to get the final answer, with some minor changes that we'll see in the inductive step. Moving to step 1, we now define the function and the states and what it's supposed to do. In this case, the function must return the minimum number of elements required to form a sum of m, with the elements of 1 to n in the given array. Note that we are again using the array index from 1 in this algorithm for simplicity. Now the recursive step is similar to what we have seen earlier, where we take a recursive leap of faith to recurse on the subproblems identified. So we have 2 choices. If we include n, we need to recurse to find the minimum number of elements to form the sum of m minus the value of the nth element using just n-1 elements remaining. And in this case, since we are including this nth element, the total count becomes 1 plus the result from the subproblem. And if we go ahead and exclude the nth element, we need to find the minimum elements required with the remaining n-1 elements to form the sum of m. And in this case, we simply recurse on the first n-1 elements with the sum as m. And finally, in the next step, we take the inductive step and we take the minimum of both these subproblem results to find the smallest number of elements needed to reach the target sum. Notice the change in the return function now. We can also simplify this statement into a single return statement just for simplicity. Now it's time to identify the base case and then end the recursion. For what states can we say that there is no need to divide it further? Just like in the previous problem, if m reaches 0, we can say that we have included or found a set of elements that sums up to the original sum of m. That is, we have found a possible way. This is one base case. Now, if m becomes less than 0, maybe we have subtracted a large number in the previous recursive step. We can say that the solution with this m cannot exist. And if n becomes 0, again we cannot go further anymore since there aren't any more elements left. Now let's add this to our code. So if we have found a solution, we return 0 to indicate that we have included the elements and there are no more elements that can be considered. For other cases, we want to ensure that the set never becomes the minimum, and thus we return int max since it will be discarded while taking the minimum of the 2 options. Note the difference in this base case and how it changed when we wanted to find the number of ways versus when we wanted to minimize the number of elements. If you notice, the only thing that changed was the return values of the base conditions depending on the problem it is trying to solve. Let's now trace the recursion tree to make things more clear. Let's take a simple example with n as 3 and m as fine. Now we can either include the nth element or we can exclude it, and once we reach the base case, we return 0 or int max depending on the base condition. Now when n equals 0 and m equals 0, we have found a solution since the sum is exhausted. So we can return 0 and each recursive node propagates the minimum of the two subproblems upwards. Similarly, when we exclude the third element, we return 0 when the sum is exhausted and the minimum is again propagated upwards. We finally take the minimum of the two subproblems on the first node to find the result. Now the time complexity is similar to what we saw for the first problem, that is big O of 2 to the power n, since each recursive node can have two child nodes and there can be n levels bounded by the length of the array. But can we optimize it further? Let's now check for overlapping subproblems. In general, if you can't clearly distinguish each recursive state, there's a good chance that you're dealing with overlapping subproblems. In both this example and the previous one, we are recursively working with n-1 elements, whether we include or exclude the nth element. Since we are also subtracting values from the target sum, it's highly likely that multiple paths might lead to the same n, m state. For instance, taking a look at the case we saw earlier, we reach the same state as n equals 3 and m equals 16 in two different ways, once by including the last element and once by excluding it. This is a clear example of overlapping subproblems and a perfect opportunity to apply memoization. Well, that's the case of overlapping subproblems, and we'll consider caching for the rescue. So let's optimize the solution in the last step. Now this is the current solution that we have. If we simply cache the return statement in a map or a 2D vector, we can use that to check if the state was already processed. Now there are n, m states, and each state computation takes a constant time, making the time complexity as big O of n cross m, while the space complexity is big O of n cross m for the memoization table and big O of n for the recursion stack. That brings us to the end of this video. I hope you liked this video, and if you do, please share and subscribe to my channel. Feel free to go ahead and check out trilab.io's problem set for more such problems, and feel free to share it with your friends as well. I will be posting more such dynamic programming contents and solutions to lead code hard problems in the future videos as well. So do keep an eye out for that as well. See you in the next video. Bye.